Welcome to Team Dr. Fluid's mechanical dissection video.
Just as we would treat helicopter propellers, wind turbines, and other unshrouded axial flow pumps, we analyzed our box fan as a set of rotating airfoils which uses rotational motion either to imbue or extract energy from the air around it. To better understand our fan, we analyzed it as a thin disc actuator and used measurements of wind speed before and after the box fan, as well as an analysis of the airfoil pitch angles and rotation rates of the system to better understand the ideal working conditions of the fan and potential design improvements that could be made.
We started off our dissection by detaching the front and back grates to remove the fan blades. We then cut one of the blades into 8 sections to measure its cross-section as it got closer to the center. Cutting these revealed that the blades are technically not airfoils, since the cross-sections do not have a trailing or leading edge, but instead had a constant width throughout. Then, using an anemometer and another box fan, we also measured wind and fan speeds at different distances and speed modes. This allowed us to compare the incoming and outgoing air speeds and determine their effectiveness, as well as calculate the angle of attack and coefficients of lift and drag.
From our geometric measurements of the airfoils and measurements of the wind speed before and after the fan, we understand the box fan as a system that draws in air from the ambient room and creates a speed and pressure difference through the rotation of its airfoils. In addition to higher wind speeds after the propellers, an azimuthal rotation rate defined by an angular induction factor also creates a twisting of streamlines after the fan.
For a box fan blade, we calculated a high Reynolds number value using our measured velocity and chord lengths. The Reynolds number indicates that inertial forces are most prominent and we can ignore viscous losses. This is supported by our assumptions of irrotational flow theory and incompressible flow.
To non-dimensionalize the characterization of our fan, we calculated the specific speed and diameter for the box fan using the equations for turbine-specific speed and diameter. We calculated the induced pressure difference through a thin disc actuator control surface analysis. We chose to do these calculations using wind speed measurements directly in front of the fan, as they are most consistent and least affected by the recirculation effects that occurred upstream of the airfoils. Using fan speed 3 as an example, we calculated a specific speed of 5.67 and a specific diameter of 0.74. As expected, we see a high specific speed and low specific diameter, since the box fan operates as a high flow rate, low pressure device. Unlike for pumps, we don't have performance and selection charts to completely inform the ways in which the efficiency and usage of the fan would change given different geometries. Instead, we can use the curves from the Envisaged propeller performance prediction charts to see that for a constant pitch angle but increasing diameter, we will quickly see a significant drop in efficiency, and for smaller diameters, we will see a more gradual decrease in efficiency.
We use the measurement of the different pitch angles along the fan blade, which are twisted airfoils. We also calculate the angle between the wind velocity here and the velocity of the fan spinning. These two terms sum up to be the angle of attack. We use the same airfoil theory mentioned in the concept part, and so that we can get coefficient of lift and coefficient of drag. By calculating the power that fan inputs into counteract the drag, we get the power input, which is part for our calculation of the efficiency. And for the power output, it's calculated by the measurement of the back and front velocity. We can tell how much energy that fan contributes to the airflow in this way, specifically in kinetic energy. Therefore, we can actually quantify which speed mode of our box fan is most optimal to work, which is the second speed mode.
The grates on the fan are designed for safety, but they also significantly impact airflow characteristics. Before the air enters the grate, total pressure is shared between the static and dynamic components. But since there's a large amount of energy loss as the fluid hits the grates, the static pressure decreases, which then reduces the airflow rate and the efficiency of the fan. In this case, Bernoulli's constant before and after the grate would be different, and this equation cannot be used when considering the grate. Additionally, separation may occur around the edges of the grate, causing turbulence downstream. Due to the high Reynolds number we calculated, we predicted a large likelihood of turbulences, meaning increased drag and energy dissipation. Lastly, we can consider how the design of the grate itself impacts the flow, specifically its porosity, which is the volume of void space over the total volume. Having a higher porosity would decrease the number of streamlines that interact with the grate. This decreases the pressure loss due to interaction, meaning smoother, faster airflow. The downside to this more efficient fan, however, is the decrease in structural strength.